Hello, everyone, and welcome to the future of space. I'm your host, Daniel Fox. Our guest today is Tanya Harrison. Tanya is a planetary scientist, science strategist, and science communicator. She's a fellow at the University of British Columbia's Outer Space Institute, former director of science for Impact at Planet, and former mission operations specialist for multiple NASA missions to Mars, including the Opportunity, Curiosity, and Perseverance rovers and the Mars Reconnaissance Orbiter, as well as analog missions with the Canadian Space Agency. Tanya, welcome to the future of space.
Thanks so much for having me.
Looking forward for this conversation, taking us to space and Mars and your journey so far. But before we go there, could you share with us 3 words that for you capture the essence of space?
I think curiosity, possibility, and boundlessness.
Maybe those are the next, well, you already have curiosity, but boundlessness and opportunity, the next rovers on Mars. Maybe you need to put those names to NASA.
It's very fitting, but I didn't even think about the fact that they were also the names of the rovers.
Now, we know that there's a science story, a technology story, an economic story of going to space and beyond. But what would you think is the human story of going to space?
I think it really ties back to that idea of curiosity. We want to strive to understand the world around us. I think we're all at heart scientists from when we're children, just kind of figuring out how things work, navigating the world around us. And then as we get older, we've done that with everything we know, right? So we have to figure out what's the next thing. What is the unknown to us at that stage of our life? And the universe is so weird and wonderful. And the more missions that we send out there, the more that we learn about it, the more fascinating it becomes. Granted, I might be biased. There's a space person thinking it's fascinating, but it has this allure that not a lot of other things have. Like if you tell somebody while you're getting a haircut or you're in an Uber ride or something like that, inevitably they ask what you do and you say, you work in space. The questions start rolling out. No one ever says, oh, that's cool. They're like, oh my gosh, why is Pluto not a planet anymore? Or what are the Mars rovers doing? I saw this article about the James Webb Space Telescope. Like, what does this thing mean? So it's this inherent thing that people want to know more about because it is such a broad alien concept to our day-to-day lives. And so I think completely separate from any political ambitions or territorial ambitions or, economic ambitions, just that genuine human curiosity aspect is so deeply tied to anything related to space.
Did you ever think that you would get to see this time that we're in where it's no more science fiction? We're not just sending rovers or drones on Mars or the International Space Station. We are actually thinking, planning, building a future of our species in space. Did you ever think that this day would come?
I think yes, but it came much faster than I would have expected. Just how much the entire space landscape has changed in even just the last 10 years with the explosion of the commercial space sector, bringing all these new capabilities that I think national space agencies would have come to eventually, but the time and the attention span required to do that is very difficult. And especially when you're working under a sort of political umbrella where the whims of the space agency are really out of their control. Whatever administration is in power at the time is really going to set that cadence compared to a company where someone like Elon Musk can say, I really want to go to Mars and I'm going to devote all my resources and all my energy to doing this over the next, 10, 15 years. It's nice to have those things working in tandem. Like you've got the government doing sort of the big things that don't have any commercial payoff necessarily, or they don't immediately. And then you could have the commercial side that's trying to figure out all the other things, or the government is giving the spark that actually kind of incentivizes the commercial side to do things. So they work hand in hand really well. But I don't think anybody could have predicted how quickly that commercial side would completely, I don't want to say overtake what the government was doing, because I feel like that really kind of discounts what agencies like NASA have managed to accomplish. But it's sped everything up and like reinvigorated enthusiasm in the public for space in a lot of different ways that we, I don't know, maybe had lost before.
We hear often that people think that like the momentum from space was going somewhere during the Cold War, and then the space shuttle, and then it shut down or really slowed down, and it took longer to get to that momentum again. But I think that we forget that even just 100 years ago, we were like barely flying up, and now we're having rockets that land upright, and we're sending. I mean, SpaceX has been sending, regularly rockets to in orbit. I think we've become a little bit. We take for granted how change happens. I mean, for someone like you who was involved in the first rover on Mars, the orbiter, and where now we have Perseverance and we have a drone. You must have seen the evolution of change and what the process of getting to make it happen, but also to see how it started small, and now we have this rover the size of of a car with a helicopter with a drone on Mars. I mean, it's amazing when you think about it, right?
Yeah, I mean, to think about how just in my lifetime, we had never landed a rover on Mars at all. Like, I remember watching Sojourner land on Mars, which blows my mind because now it's something we take for granted. There's been rovers continuously operating on Mars since, I guess, since Spirit and Opportunity landed back in 2004. So it is something to kind of say like, well, we've always had Mars rovers. For a lot of people that are alive right now, they don't really think about it. But going from Sojourner being a technology demonstration, it wasn't even we're sending a rover to, find out the history of life on Mars. It was, can we rove on Mars at all? And then building on that to say, okay, yes, this works. And now we're going to build bigger, more complex rovers to follow the water to see if we can figure out what the climate used to be like. And then evolving again with something like Curiosity to say, okay, we're going to look for signs of habitability because now we know the water was there. Was that water conducive to life? And now with Perseverance, we've taken that big leap. Okay, we're finally looking for signs of ancient life once we get those samples back from Perseverance in sort of the 2030-ish timeframe. And I think that those samples are going to completely revolutionize our understanding of Mars. And I think kind of taking a step back, that does seem like a very long time. Sojourner landed in 97. It's going to be 2030 before those samples come back. But this is a very long process to design these missions, build them, test them, get them to Mars, and then drive around and figure out like where are the spots that have those clues that we need to find. Because it's not like you're just going to land and there's the rock right in front of you that holds the key to all the answers that you want to know about the planet. But seeing how much that has progressed and how we've taken all of the lessons that we've learned, both from a science and a technology aspect on each mission and then applied it to the next one, it's such a beautiful illustration of how science and exploration work. And so I love to kind of look at that, the through line of the story of all those missions working together in tandem.
Now, were you always, when you were young in high school, was that where you wanted to go with your life? Were you like, you woke up, or you ended to your high school and you said, I want to work for Mars, sending rovers? I don't know. What was your vision of your working path, of your career as you left high school?
I was like, as soon as Sojourner landed, I was completely obsessed with Mars. I was like, I really want to work on Mars rovers. I didn't necessarily know at the time exactly what that meant. I think initially I wanted to be an engineer. I was really obsessed with Star Trek. I was like, I want to be like Geordi, but I don't make a good engineer. I'm not very good with like physically assembling things. It's just not my skill set. But more of like an understanding of how systems work. I realized that's more where my brain is at. Like I could draw circuit diagrams and totally understand them, but taking that and applying it, like putting it on a breadboard in like circuits classes in college, I for some reason I just like couldn't do it. My brain couldn't put those two things together. So I realized I was not going to be an engineer, but I did like science. But in school, like in junior high school, like I still have to this day a piece of notebook paper where it was in like I think grade 8 health class. For some reason we had to write our name on the top, and then we passed the paper around and people had to write a comment about you or like what made them think of you on this piece of paper. Either I think most of them are anonymous, but 98% of the things on that paper have to do with Mars. And I think the other 2% have to do with Star Trek. So it was something that everybody kind of like associated with like my identity, which I just found it going through like scrapbook stuff when I was packing to move a couple moves ago. And it made me smile. I was like, wow, okay, I'm glad that like even when I was like 13 or something, people are like, oh yeah, she's the Mars girl.
And then you took it to NASA and you knocked on the door and they said, I want to work for you guys.
Basically, like I was getting near the end of my master's program and I was intending on going to get a PhD because at that point, like the commercial space sector didn't really exist yet, other than, you know, Boeing and Lockheed. But again, as a not engineer, that's not really necessarily a job opportunity for a geologist. And so, but my grad school experience through my master's was not pleasant. And so I was like, I don't think I want to stick around and do a PhD. So I just started emailing all of the authors of papers I had read for my research to see if any of them needed like some kind of data processing lackey, because I had done that as an undergrad with astronomy data sets from like Hubble Space Telescope and some ground-based telescopes. And I really liked working with the raw data. Like it's one thing to do research from all these different space missions with data that's already been collected and handed to you. It's something very different to be like the person that's actually collecting the data. And I thought that was cool because it's such a limited number of people that get the chance to do that. So someone had suggested, well, maybe you should work in mission operations. Like that kind of sounds like it would be up your alley. And one of the people that I had emailed said, oh, there's this company in San Diego that like is the NASA subcontractor for building cameras for Mars missions. You should take a look. I never would have thought to have looked at them on my own because, again, why would anybody at a company that builds cameras need a scientist? But since they did mission operations at the company, they were hiring for staff scientists who were the ones that would actually like target the cameras, process the images when they came down, look at them from the technical standpoint, like is the camera functioning properly? But also from a science standpoint, is there anything in this image that's telling us something important about the history of Mars? And you could do science if you wanted to, like writing papers and going to conferences and whatnot, but it wasn't required. And so that actually made it fun. Like the science was the stuff that I could do when it wasn't my week to be targeting the cameras, because we kind of switch off between redundant people week after week. And that was like, to this day, that's still the coolest job I've ever had. And I think part of me would have been completely happy just doing that every day until I died. Like coming in, taking pictures of Mars and like getting them back and seeing them and being like, no one else has seen this picture of Mars. No human on the entire planet has ever seen this picture. And like, I got to take this of another planet. And for a few minutes, I get to stare at this and no one else has seen it. Like, that's really, really cool and a very rare opportunity to have. And I feel so lucky to have had that experience. It's just amazing.
Did you have a special inbox from Mars where like the first images would come in and then you would have the little notification on your computer, ding, just the image just came in, and then you were the first one, right? You were that landing point for these images to come from Mars, right?
Yeah, you would get basically all the images for each day kind of come back in one uh, like deep space network pass, essentially. So you get an email every morning, Earth time, that would say, like, 18 pictures taken by the context camera CTX the day before. And so you like run a little command and they would pop up, and you could just basically just sit there with your arrow keys and kind of go through them for each day, scroll through. We all had 30-inch monitors because the images, like, kind of displayed at half resolution, would take up the entire width of a 30-inch monitor. And this is in like 2008. So these are, like, for the time, massive monitors. So we would put two side by side so you could see the whole image at full resolution and just scroll through it. So you're literally like wrapped around in Mars, just immersively experiencing the landscape every single day.
How long did it take? I mean, I'm pretty sure the speed of downloading has increased tremendously over the years, but how long did it take at the beginning for an image to be sent from Mars to Earth, and how long does it take today?
It's really highly dependent on how far away Mars is. And so I don't remember the exact data rates. There's actually a Twitter feed called DSN status that shows you what dishes are talking to what satellites in real time. And for Mars Reconnaissance Orbiter and Voyager and some of the other missions like that, it'll actually show you the data rate, and it'll say like 120 megabits per second. Or in the case of Voyager, it's like, zero point zero 0.01 megabits per second. So it's very slow. But I tend to think of it in terms of, like, because the camera that I worked on for the longest and was like most involved with was the context camera on Mars Reconnaissance Orbiter. So when Mars was at its closest, like a 4-minute one-way light time, we could get back maybe 300 to 500 images every day. So that took a really long time to go through. But then if Mars was at its like near conjunction, so the other side of the sun, we would be lucky sometimes if we could get back 3 images per day. And that's when you got the time to do a lot of science, because you'd look at the 3 images from the day before and you're like, okay, well, now I have nothing to do for a week, so let's write some papers.
And during your time over there, can you share with us, like, one of your biggest unexpected discoveries where you looked at it and you're like, oh my God, this is the proof of whatever we thought, or we didn't even think of this. I mean, I assume there are many of them, but is there one particular one for you?
There is. So if you look at a map of Mars, the southern hemisphere is, covered in craters, but the northern hemisphere is pretty full of broad, flat plains. Like, at first glance, it doesn't really look like there's anything there. There's not even that many craters on it. But there's one particularly large crater called Leo that is the youngest of the large impact basins. So, like, bigger than maybe 200 kilometers in diameter on the entire planet. And when we decide where to take pictures with the context camera, you kind of run any space mission under the assumption that it could die tomorrow, because you never know what's going to happen. Cosmic ray hit, bad command, some moving part fails. So we would image Mars in priority order, basically. So let's start with the most interesting sites geologically. Let's image the rover landing sites, potential future rover landing sites. So the broad, like, featureless northern plains were a very low priority. But MRO, Mars Reconnaissance Orbiter, MRO, operated for so long that we mosaicked all of those interesting parts. And so when we would get to these high data rate periods where we could take hundreds of images a day, we had to figure out, like, it was hard to fill the buffer. Like, we're picking images left and right. And so we had imaged all of Leo. So I started imaging the ejecta blanket from it, and going through the images one day, I'm scrolling through, and you have like the crater and the ejecta blanket, which is all the stuff the crater spits out when the crater forms. And at the very edge of it, there was this huge outflow channel. I thought, oh, that's really weird. And looking at other images, and like, you can't really see it in anything other than these context camera images. So I followed it as far as I could, and then I started planning other images in that area and ended up finding this entire network of outflow channels that all started at the edge of the ejecta blanket of this crater. And they covered an area the size of something like the state of New Mexico. It was massive. So it looks like what happened was either this crater impacted into a layer of buried ice and then like melted it, and that got caught up in the ejecta blanket and created all these little not so little floods. Or there might have been liquid water, like groundwater in that area when the impact happened, and it like liberated all of this water, and it either like flooded immediately or mixed up with all that rock and stuff in the ejecta blanket and then de-watered, which happens a lot in landslides. So like you have wet dirt that slides down, the dirt stops, but the water in it kind of percolates down and then like flows out the end of the front of the landslide. So either way, it tells us that there was water in some fashion, and a lot of it in this area in a relatively young, like 3.5 billion years ago. It's not that young, but for Mars, it's significant. Water or ice in this kind of middle latitude region. And it was completely unexpected, like total accident, just because we happen to have enough room in the buffer to image this area. And I ended up like mosaicing the whole area, analyzing the images, writing the paper, and getting it reviewed and published in like a 5-month time span. It was super, super fast.
So it is your belief that there is a lot of ice or water on Mars?
Well, now we know for sure there's a lot of water, at least buried ice in the middle to high latitudes in the northern hemisphere, because we found impact craters, like new impact craters. So we have images where the crater isn't there, and then days, weeks, or even years later, another image where the crater has formed. And some of those were actually excavating ice from the subsurface and depositing it on the surface for us to see. So we started mapping those out and figuring out where the cutoff was. And it seems to be around 40 degrees north latitude. And there's been dozens of these found at this point. And there's 2 radar instruments, ground penetrating radar instruments in orbit of Mars right now. One on Mars Express, which is a European Space Agency mission that's been there since 2003, 2004. It's like the second oldest still operating mission at Mars. And then Mars Reconnaissance Orbiter has one too. And with both of those, we've been able to detect subsurface ice deposits, or like the European Space Agency mission found maybe a subsurface muddy lake near the South Pole. It's a little controversial. There's some other things that it could be, but there's a lot more buried ice on Mars than I think we knew about for sure just 20 years ago.
And even on the moon, the Chinese samples that just came back that apparently confirmed there's a lot more water. I wrote this article suggesting that our expansion in space will follow the same logic that we took on Earth, which means that we followed the water. We explored, and then we took the rivers, and then we settled in these places that made sense because of the water, because this is really what we need the most. And it will follow that same logic as we go to space. We will follow the water where it is on these planets. And so we'll spread, along these rivers of waters in space. And is that something that you think was going to happen?
Absolutely. And the cool thing is, I think we maybe, even in the 70s, 80s, the idea was probably water is going to be the limiting factor for humans going out into space, because we didn't know that it was all over the place. And now it seems like anywhere we look, there's water on the moon, on Mars, tons of these moons in the outer solar system, on some asteroids like Ceres. So maybe water isn't actually the problem. And from water, we can make breathable oxygen, we can make rocket fuel. So maybe that's actually not something we have to worry about. So then the question is, well, what are the other factors that limit what humans can do as we expand to these other bodies? But it seems like water is almost everywhere. I think they even found water on Mercury, which is mind-blowing.
I was talking to a geologist, and now they're able to find the water molecule in rocks in a different composition, not composition, but state. But if the molecule is there, then there's a way to extract it and then create water. So even when it doesn't look like there's water in the rock, there's actually the molecule is there. Did you come up on that piece?
Yeah, I guess when geologists say water, it could be like the molecule H2O, which we're used to on Earth. It could also be what's called hydroxyl, like OH. So when we say like hydrated minerals, sometimes it could be either one of those things. But it's probably something most people that are not geologists really think about. But if you go and pick up like gypsum, for example, that's a mineral a lot of us know. It's in drywall in buildings. It's at museums. It's always in hippie crystal shops. Like everybody has seen it probably in some form. Gypsum is calcium sulfate with 2 water molecules in its structure. But when you look at it, it's a rock, right? You wouldn't think of this as something that's wet. But you can heat that up. You can break those bonds in ways to separate the calcium, the sulfate, and the water, and theoretically extract water from that. And that's just one example of tons of minerals that have water in some form in its structure. And so that's another place where we can look for this, even if we don't see, giant ice deposits like we do on the moon or Mars.
Wow, incredible. Now, so you went from working on the missions on Mars, and you became the science impact at Planet, following a big discovery. I mean, these kind of discoveries that you had when you were working on Mars. Can you share with us, collecting the data, working in a company that collected satellite data, what was another discovery that was unexpected?
Ooh, that's a good question. I feel like on Earth, fewer unexpected things happen because we're so aware and monitoring lots of stuff. I guess I can give a natural example and a human example. A natural example was there was I'm trying to remember what year it was. I think 2018 or so. There was a very massive earthquake in Indonesia. And usually when you're trying to analyze the effects of earthquakes like this, it takes a lot of time because you have to go out on the ground and survey damage. You don't necessarily have satellite imagery from like right before and right after the event happening to be able to say this happened because of the event. But since Planet takes images of the whole world on a near daily basis, you had that data set to work with. And so you could see in the images that the ground in some places moved by up to 10 meters, which is like usually when you're talking about plate motion on the Earth, you're talking about a couple centimeters a year. And you had 10 meters of like sideways motion in the span of like 60 seconds. So, of course, this was extremely destructive, triggered a bunch of flooding in the area, a lot of destroyed infrastructure. It decimated a lot of rice paddy farming in the area, which in turn triggered a bunch of these what's called soil liquefaction mud flows. Basically, the ground shook so much and it was so wet that the dirt just turned into a liquid and flowed all over the place. They're very, very destructive. And being able to like see all of this immediately before and immediately after this earthquake from space is pretty mind-blowing. And then on the human side of things, there were folks that were monitoring the kind of the area around the border between Russia and Ukraine, like before the war technically started. And I can't remember which institute they were with, but they might have been with the Middlebury Institute. They were analyzing images and they could see from the images that Russia was ready to like invade the country in specific areas based on like where tanks were lining up and movement of different types of vehicles. And they said, we think this is going to happen. hours before it actually happened and then broke on the news that Russia had invaded Ukraine. So it kind of emphasizes the idea that like it's really hard to hide from space. Like you can't really be all that covert anymore.
And there was also the when the volcano in the Pacific Ocean that was captured by satellite. Was it a Planet satellite that captured that, or was it a different company?
Yeah, so we had actually been monitoring that volcano. It's called Hunga, Tonga, Hunga Haʻapai, if hopefully I pronounced that right. There were folks at NASA Goddard that were studying that volcano. It appeared from under the ocean back in 2016 or so, and so this scientist at Goddard had been monitoring it ever since. And he pinged us and said, "I think there's some activity happening in this volcano. Can you regularly monitor it for me?" And since it's kind of like it was really small and not like part of the mainland, it wasn't something that was like in the imaging map regularly. So we had to go and manually add it. And so since we were imaging it for him, we managed to capture the volcano in the days leading up to the large eruption. And this didn't really make the news quite as much, but before the big one, like the day before, there was actually a smaller eruption that was still quite large that took the caldera that had been above the water, and the middle of the island blew up, and now the caldera was below the water. And that's why the large eruption was so destructive, because you have essentially like superheated gas mixing with water, and that's really bad. So if that first eruption hadn't happened to get it below the water, the second one wouldn't have been such a dramatic event.
It's absolutely incredible to think of all the information and the knowledge that we're able to capture without being physically there. Like for me, you read stories, or I was just recently, down south in Antarctica or up in the Arctic, and you read these stories of explorers that physically had to be there to collect the weather, the having an expedition in the winter in Antarctica in a small cabin at minus 50 or 60 just to collect the weather, because you want to know what is the weather pattern. The human cost of seeking and gathering that knowledge. And now today we have these machines that are able to flood us with so much knowledge that even that by the time that we go there, that we go to these places, the humans will not be exposed to such risk as it did before. I think we live in an incredible time. I mean, just even the James Webb Telescope, that it's in an orbit that we've never physically been there. It's just mathematically, it makes sense, and enough that we're willing to send a multi-billion-dollar telescope and know that it's going to go, it's going to work properly. I mean, we're entering an era that is just going to, I think, redefine what it is to explore these remote places. I mean, you must be excited about what's coming.
It opens up so many opportunities for people to be involved in exploration at large that would never have had the ability to do so, whether it's because of disability or financial restrictions, or because they have children and can't say, I'm going to go off and explore Antarctica for 8 months. Bye. There's so much opportunity there. And the fact that you can sit on your computer wherever in the world you might be, as long as you have an internet connection, and explore the entire Earth. Or since all the NASA data is public domain, it's a free and public good that's out there for anybody to use. There are tons of different interfaces where you can go and explore all this data that's coming back from Mars and the moon and Juno, which is at Jupiter right now. It's completely revolutionary. And I think that leads to some people arguing and saying, well, doesn't that mean we don't need to send humans back to the moon or to Mars, because we have these rovers and these satellites, so can't they just collect all the data we would ever need? And I think there's flawed logic there. Like, yes, it's expensive to send humans. Yes, it's dangerous, but we never get the complete picture from just doing something remotely. And I think anybody can relate to that, just even on a personal standpoint. Like, looking at a picture of a beach in the Caribbean is very different from going there and having that experience yourself. And so we shouldn't cut ourselves off from the human experience of going to these places and being able to physically pick up a rock and turn it around and look at it in the context of the landscape around you. Being able to do that is so different and so valuable compared to just looking at a photograph from 200 million miles away.
Yeah, I was so annoyed by that paper by these two scientists who thought that, like, so now that we have machines, there's no need for human exploration. We can just send. I'm like, no, you don't get it. It's actually going to make it even more enticing, because now we can send those devices to scout for us, and then we can show more easily without risking our lives. Now, Tanya, you were working at Planets. You're not anymore. You're taking a break. Are you in a capacity to share with us what's next on the table for you?
So I'm taking some time to work on kind of a research project, but in the less like Mars geology specific sense. And instead, I'm trying to look at how we can bring together two different groups that tend to be kind of at odds with each other: the space exploration community and the environmental community. And this was very much influenced by the experience of having spent, 12 years or so working entirely on Mars, and then coming and working in Earth science at Planet, and with a very heavy environmental focus, and just seeing the rhetoric on both sides. There's often a very negative perception of space exploration from the environmental community, because they think, well, this is a waste of money. Why are we spending money on other planets when we have problems to solve here on Earth? But it also tends to be a very negative narrative. It's, oh, humanity is doomed. We've screwed the Earth. Like, we shouldn't go to Mars and just screw that up too. And that's not a good way to motivate people. There are tons of studies that show this. Like, yes, it generates a lot of like social media activity to have negativity, and that's why this kind of thing tends to get fed to us through algorithms. But actually triggering action, it's much more effective to have positive messaging. And I think this is where the space exploration community really excels, because even though there are some like very fanciful ideas out there, and some of them are very like completely unrealistic, or at least unrealistic in the short term, it's generally a very positive thing. Like, wow, we can do this. We can build these rockets. We can build habitats on Mars. We can explore the origins of the freaking universe with a telescope, like you said, that we launched into an orbit that we had never even tried before. Like, that is amazing. And you can see how much that motivates people. Like, everyone in the space sector, I shouldn't say everyone, almost everyone you'll meet in the space sector tends to be like an extremely passionate person that has gone into it because they want to see a better future for humanity. And that's exactly what the environmental community at the core wants too. They want a better future for humanity. They just want it on Earth, which is very important. And so I think that there are lessons that each side can learn from one another in this dialogue. Like, the environmental community tends to focus a lot on activism and policy change. And I think that while that kind of stuff does happen in the space exploration community, it's not quite the same. But I think that the positivity of the space exploration movement, like, if that could infuse onto the environmentalism side, like, can we all come together and say, hey, at the end of the day, we're all trying to accomplish the same thing through different routes, and the stuff that's happening in space has direct benefits to environmentalism, both in the direct sense of things like Earth observation technology helping us monitor the planet, as well as the idea of the technology you need to develop to survive on Mars is the same technology you need to combat climate change on Earth, stuff like carbon capture technology. So don't be at odds with each other anymore. Like, let's sit down at the table. Let's talk about how we can work together to further that goal of having a happy, healthy, sustainable future for humans wherever in the universe that might be.
You're speaking my language word for word. I mean, this is exactly what, the future of space and the stories that I've been writing. I mean, I used with Field of Wild my past 15 years. all my writing was about trying to reconnect our species with nature, but also celebrating our species. We're not, the human species is not a bad species. Life is just messy by design. You know, there's no differences in the path to an innovation, to a path of a mistake. It's just the hindsight that tells you, well, that was a stupid idea or that didn't work. But going over there, it's exactly the same thing. And unfortunately, disruptions and tensions and pushing the boundaries of your environment is part of nature's process for evolution. That's how it moves forward. The human species is expert at going beyond these limitations, but again, the process is messy. And the thing that for me, I've always try to work against or change is that narrative that the conservation and the movement or the environmentalist movement have done, portraying the humans has this element of the equation that if you could take out, everything would be perfect, and we're such a negative asset to to the planet. When in reality, we're not. We're actually one of the best asset in that equation, because from, not that I want to personify the planet and life, but from the perspective of life, we're about to give life its biggest gift in 3.6 billion years. We're about to take it to the universe, because it would be a shame for an entity like a planet to develop life and for life to grow in complexity all this time, only to be destroyed because of whatever, randomness of the universe, or just the sun, in some billion years. The scale of the universe is grand because it wants to populate and it wants to expand, and we're that key that's going to make it happen. So I would I don't know if I don't think that you were at South by, no, you were at South by Southwest, correct?
Not this year, unfortunately.
Oh, not this year. There was, Patagonia had taken an entire side of a building with a giant ad of a wave, the ocean wave, and written in giant letters, "Not Mars," and in smaller print, "We are in the business of saving the planet Earth," and it was Patagonia. And I felt that it was such not even useful, but just not productive, and for a company who's often so quick at showing how good they are, that it was not contributing to anything good, to divide, to polarize even more, as if anyone who's involved into space technology or Mars technology are not for the care of the planet. And let's not forget that Patagonia is in the business of selling clothes with a conscience. They're not in the business of saving the planet. But I think that what you're doing and what we're doing at the Future of Space is really what is needed to bring to the table and talk about the future of our species within the context of outer space, but for the benefit of the Earth, as opposed to thinking that these two are against each other. I love what you're getting into, Tanya. Now, the segue to that, and I want to be mindful of your time, with an amazing career already and where you're going. For you, what would be your 3 words of wisdom for anyone who's listening, and either they're young and looking for their next move, or they're older? What would be Tanya's words of wisdom? 3 words.
It's funny, the first word that came to mind is another Mars rover, completely by coincidence. I'd say perseverance, hugely important. Focus, very important. And hope.
It's I think that's really what brings the human experience. I think that we have a capacity to rewrite our tragedies and the places of challenges and create hope in the process. I mean, we've been through such incredible tragedies in our evolution, and somehow we are able to come out of it and make the best of it. COVID was obviously one, but I think that, the wars and the famines and these diseases, and somehow we are where we are today. And that there's a lot of talk right now about AI that's going to, transform the world and will eradicate humans. But I think that we don't give ourselves enough credit for our capacity to figure a way forward and come out of it better than when we entered in it. Tanya, I'm really looking forward to see what you're going to be coming up with in the next year or two. This is fascinating, and I thank you so very much for taking the time to be with us today on the Future Space.
Thank you so much.